Let's go to lecture objective 6. This is to look at the hormone balance and how two major hormones control our metabolism. So the absorptive state versus the post-absorptive state. Now, overall, we want to think about the body as being able to store additional energy whenever it needs to put energy away for future use, right? Whenever it predicts that food or energy may be scarce. So the body evolutionarily is built in that way. And as you probably know, we can store as much energy as we can consume. In other systems, there's much more of a homeostatic balance. But with the gastrointestinal system, the homeostatic balance is a little skewed in that you can absorb and store as much calories as you can physically ingest. So the body's evolutionary built to have two states that it can use in terms of that protective mechanism. So the absorptive state is when you're fed. This is right after you've had a large meal. Your body is in the state of storing macromolecules. It's um, breaking down the food components that you've eaten, and it's liberating energy or ATP, and it's storing that away in the form of those biomolecules. Now, alternatively, the post-absorptive state or the fasting state, this is where the body has gone for a period without food, and now it is looking for energy stores in those reservoirs that it has, stored away from the fed state. So this is the state where the body is not able to get additional food and it's tapping into the stores. So we'll look at the hormones that help to regulate both of these states. So in the absorptive state, energy input is going to exceed energy output, right? So again, think about Thanksgiving, you had a large meal, or early in the morning you had breakfast. Glucose is going to be the primary source for most of your cells. So your cells will take any glucose that is immediately available and it will use whatever it needs immediately. And then the rest of that will be stored. It's going to be stored in the liver, in the muscle, some parts of the kidney, and then in fat, right, in your adipose tissue throughout the body. So this is a schematic that shows the absorptive state. So you absorb a small amount of that, right? You have absorption of your small or micronutrients here that enter the bloodstream through the gastrointestinal tract. And then glucose is what the body prefers. So most of your body cells will immediately utilize the glucose that's available for what they need at that time. Then the rest of that gets stored. So glucose can also be stored in the liver and muscle as glycogen. And then that can also be stored in the fat that can be converted by way of triglycerides. So glucose can help build the glycerol backbone, and then fats that you've ingested can help build the fatty acids, and together those can be stored away as triglycerides. And then any protein that you've eaten will be broken down to amino acids that can be stored again in the liver as fatty acids and then converted to produce triglycerides, or it can be stored directly in your body's muscle as protein, right? Stored into muscle. So this is how your body, again, uses what it needs immediately and then stores the rest away during the fed or absorptive state. Alternatively, we've got the post-absorptive state or the fasted state. This is where your energy output exceeds your energy input. Now, the brain is really picky in terms of its energy source and it prefers glucose. So when you're in this post-absorptive or fasted state, your body is going to utilize any glucose. And so your brain, excuse me, is going to utilize any available glucose and it's going to be spared, particularly for the nervous system. Other tissues, however, muscle, liver, most of your other body cells, they can use fatty acids. They can use fatty acids, they can convert them to ketones usually, and then they can use that as a source of ATP production. So you're going to be breaking down nutrients and using whatever you can find. You're going to break down glycogen, you're going to break down fatty acids or fat, and you're going to liberate energy to be able to use that. Now, proteins are not usually broken down as the first line of energy source. Protein, or your body's muscle source, is sort of the last reserve. So you're really going to have to tap into a really energy deficient state, a really malnourished state, in order for your body to begin to tap into protein and break that protein down, right? So the body prefers glucose and then fats. So looking at the schematic for the fasted state, so now you're looking at all of your storage macromolecules. So you can break down muscle. Again, this is the last resort or last reserve. So proteins can be broken down to amino acids, and then amino acids can be used by non-nervous tissue. Again, most of your body cells as a source for energy. Now, the preferred sources are going to be glucose and then glycogen. Glucose and then fat, excuse me. So fats can be broken down. Triglycerides can be divided into the fatty acid component and the glycerol backbone. The fatty acids can be broken down directly, and then they can also be shuttled to make ketones. So can the glycerol, and then that can be used as an energy source. Now, ketones can be used by most of our body cells and to a lesser degree by nervous tissue, right? Most of your body cells will typically use the ketones, and then the brain will prefer glucose. So we can break down glycogen stores in the liver, glycogen stores in the muscle, and liberate glucose, and that can be used preferentially by the brain and then to a lesser extent by other non-nervous tissue, but it's really spared for the brain. Okay, now when you look at those two states, they're antagonistic, and so we want to think about the hormones that are going to turn those states on and off. So the two hormones are insulin and glucagon. Insulin is the hormone of the absorptive state. So insulin signals to your body, we've got molecules, we've got food sources, we have energy to be stored. Let's use what we need and let's store the rest away. So whenever your insulin is high, your body is in a storage state. It's going to be storing that energy as fat, as glycogen, as protein in the form of amino acids. Glucagon, on the other hand, is the hormone of the post-absorptive state. So whenever you're devoid of food, your body will have high amounts of glucagon, and that will trigger your metabolic processes to break down protein, break down glycogen first, then fats, and last resort would be protein. So glucagon is the hormone of the fasted state. Other hormones play a role, such as epinephrine and the sympathetic nervous system. These two can also play a role in the fight or flight response, in the absorptive state, in the post-absorptive state, which is the glucagon state, as we'll see coming up. Now, when you look at the role of insulin, insulin is secreted by the pancreas. The pancreas is one of our gastrointestinal accessory glands. It actually has both exocrine and endocrine portions. So the endocrine part of it is the islets of Langerhans, which are these clusters of cells that are in between the exocrine part. The exocrine part is the acinar cells. So these cells release enzymatic secretions. So enzymatic enzymes, not enzymatic juices, excuse me, like lipase, amylase, those are released into the gastrointestinal tract by way of ducts. So that makes it an exocrine gland. The islets of Langerhans, however, notice they have lots of capillaries, lots of blood supply, because they release the hormones here into the bloodstream. Hence, they are endocrine glands. Now, insulin is secreted from the beta cells of the islets of Langerhans. And the function of insulin is anabolic. So it's going to be building up or storing up. So that's going to be glycogen synthesis, glucose turning into glycogen, triglyceride synthesis, so fatty acids and glycerol converted to triglycerides, and then it's going to promote glucose usage for storage. So immediate glucose uptake. Any immediate use of the cells, if your liver cells, kidney cells, or other general body cells, muscle cells, for example, are requiring glucose, they're going to immediately take that up from the blood under the influence of insulin as well. And then overall, it will decrease catabolism. So breaking down of those greater tissue. Breaking down of those greater molecules. So breaking down of proteins will be turned off, breaking down of glycogen turned off, breaking down of fats will be turned off. Looking again at some of the other triggers or responses to insulin, it's going to increasing glucose plasma is going to trigger insulin release. So whenever you have food coming into your GI tract, glucose coming into your bloodstream, into your plasma, that will be a trigger for insulin release. Increase amino acids. Again, if you've had a lot of protein ingestion, that can also spike your insulin release and release the trigger being amino acid in the GI tract. The parasympathetic nervous system, so excitation of the PNS, again, the rest or digest division of the nervous system can trigger insulin release. And then the hormone glucose-independent insulinotropic peptide or GIP, which is triggered whenever food comes through the gut. That is another trigger for insulin release. Now, secretions decrease during the post-absorptive state. So whenever you have the fight or flight state, you actually turn insulin off. Glucagon is going to be the hormone of the fight or flight state or the post-absorptive state, and that will trigger the sympathetic nervous system as well as the release of hormones, epinephrine. So looking at the overall role of insulin secreted from the beta cells of the islets of Langerhans in the pancreas. So an increase in insulin secretion or insulin release is going to cause most of your body tissues to increase their glucose uptake. Excepting the brain, right? The brain is going to prefer glucose. So increase in glucose uptake, increase in amino acid uptake, increase in protein synthesis, and then increase in protein breakdown. So this is how the body uses what it needs, stores the rest, and it's going to turn off the catabolic processes. The processes of breaking these things down will be turned off in favor of anabolic processes. In the fat tissue, it's going to increase fatty acid synthesis and decrease lipolysis. In the liver and muscle, it's going to increase glycogen synthesis and decrease glycogenolysis. And then in the liver, fatty acid synthesis also increases, and gluconeogenesis is going to be decreased or turned down. Gluconeogenesis is the process of turning proteins into glucose. So that's kind of the cross pathway of making new glucose, hence the neogenesis from protein source. So that will also be turned off. Let's shift and look at the role of glucagon. So glucagon is secreted from a different set of cells here, the alpha cells of the islets of Langerhans. And this is going to be promoting glucose sparing for the nervous system. So this is encouraging the glucose to be sort of shuttled off to the brain and spared for the brain tissue. And then other functions of glucagon would be to mobilize energy stores, stimulate or enhance glycogenolysis, breakdown of glycogen, lipolysis, breakdown of fats, and then the stimulation or production of new glucose from protein sources, which is gluconeogenesis. And so glucagon will be turning on catabolic processes and then turning off any anabolic or building up processes, right? It's going to be breaking things down, liberating energy for ATP. So some of the triggers or stimuli for glucagon secretion would be the overall post-absorptive state, so just being in a fasted or a prolonged state without food, which is triggering your fight or flight response. So the fight or flight response, the cortisol response sort of goes hand in hand with glucagon and the fasted state or the post-absorptive state. Another trigger will be to decrease the absorptive state. So any decrease in the absorptive state, which is going to be more along the lines of increase in glucose in your plasma. So that will actually turn glucagon off if you do have glucose coming into your GI tract, glucose being absorbed into your plasma, or if you are in the fed state. So again, the alpha cells are what make glucagon, and the alpha cells, just for reference, are usually around the edge or the periphery of the islets of Langerhans, whereas the beta cells are typically usually in the center. Now, the alpha cells will trigger several glucagon release, which triggers several different responses. So glycogenolysis, breaking down glycogen to make glucose, and then decreasing glycogen synthesis, which is the opposite. Gluconeogenesis, breaking down protein to make new glucose, increasing ketone synthesis from the use of fatty acids, and then increasing protein breakdown or proteolysis, meanwhile decreasing protein synthesis, which is going to be the anabolic process. So it's going to be activating catabolic processes and then blocking the anabolic processes. Okay. In terms of your fat tissue or adipose tissue, it's going to stimulate lipolysis, which is breaking down those triglycerides into fatty acids and glycerol, and then blocking triglyceride synthesis. So as you can see, glucagon is going to help your body break fat down. It's going to actively stop fat production or fat synthesis and actually tap into those fat stores so that that can be utilized as a primary source for metabolism and for ATP production. So if we look at our two hormones, insulin is going to help your body store fat away, and then glucagon is going to help your body liberate that fat for energy. And if you think to some of the dietary trends around metabolism and around this understanding, if you rely on your insulin hormone and sort of lowering your insulin hormone, that can be a good way to promote good use of glycogen in your body, promote glucose utilization, and help your body actually use the glucose that's already existing. And so that can be important for diabetic patients and for obesity, is just understanding how those hormones really unlock the ability to store and utilize fat, right? So if you look at our blood glucose levels, so blood glucose levels are going to be really important in terms of determining whether insulin is released or whether glucagon is released. So your normal blood glucose should be around 70 to 110 milligrams per deciliter. That's kind of where your body should be normal, and this is fasting. And then if you're hyperglycemic, at a fasting state, your blood glucose is still very high. So it's at 140 milligrams per deciliter. So imagine being in the fasted state, but still having excess glucose, really just, inundating or swimming around in your plasma, in your blood. And so insulin release is going to be really high, although you're in a fasted state, which is what pretty much type 2 diabetics will have. You can also have type 1 diabetes, which is where your body doesn't make insulin, and that will be a similar presentation of really high glucose levels, even in the fasted state. Now, hypoglycemia, on the other hand, is low glucose levels. So glucose of less than 60 milligrams per deciliter is going to be hypoglycemic, and that can lead to various consequences, such as coma, such as ketosis or ketoacidosis, and then even death. Okay, so it's really important to have adequate blood glucose levels, and those are maintained by the actions of the insulin and glucagon. Now, if we look at the trigger of glucose release, so let's look overall at what happens when the body releases a lot of, or ingests a lot of glucose, and that is released into the blood, that is absorbed rather into the blood. So the first trigger is for insulin to be secreted from the beta cells. Now, after that, insulin is going to stimulate most of your tissues to uptake glucose. And then it's going to stimulate your liver and muscle to store that away as glycogen, meanwhile blocking the breakdown of glycogen or glycogenolysis. In your liver, it's going to block gluconeogenesis, again, preventing any new sources of glucose to be made. So insulin is basically telling your body, let's store this energy away and let's block any processes that would make that will break down or make any new sources of energy. And so it's going to help to decrease your blood plasma glucose, your plasma glucose levels, all right? So the overall result of glucose should be insulin release and decrease in plasma glucose, so that that glucose can be absorbed into your cells, used immediately, and then stored away for later use, okay? Now, the other schematic, I've left this blank because I want you guys to work on this as homework or as extra practice. So think about the appropriate response for the opposite of this. Let's say you have decreased plasma glucose. What is the hormone that would be released? What is the effect that you would see in your liver and muscle cells? And then what is the effect that you would see in your fat cells? So think about drawing this out and filling this out on your own, and then we'll discuss this when we meet next time, or I'll post the answers so that you compare your answers to the actual chart. So this is just extra practice to compare the opposite of increased plasma glucose and think about how the hormone and the various effects would differ.